Forces act on objects all around us. These forces cause objects to move at various speeds. When a force like a rocket engine causes a rocket to move, its velocity changes depending on the magnitude and duration of that force. There is a mathematical tool we can use in situations that involve force and time, such as vehicle deceleration and collision, or forces from motors, springs, brakes, gravity, and friction.
Hello, my name is Norman Reese. I teach engineering here at LeTourneau University, and I want to talk about a principle that we can use to solve these problems involving force and velocity, and it comes from Newton's second law of motion. So force equals mass times acceleration. Now we can rewrite this a little bit to be m dv dt, because acceleration is a change in velocity with respect to time. So I'm going to bring this dt over here, so I have f dt equals m dv, and then I'm going to integrate both sides. Okay. Now when I integrate m dv, since mass is a constant, I'm just going to get m v2 minus m v1. I'm going to bring that mv1 over to this side of the equation. That is going to equal mv2. This is the impulse momentum principle. And what it's saying is that the mass times the velocity in the initial state, also known as momentum, can be affected by force that's applied to that body over an amount of time. So the integral is going to sum the force over that amount of time. This is going to give us a new momentum, mv2. Now in physics class, you might see it this way. We have an initial momentum, I, they'll use p for momentum, plus the integral of f, perhaps f net, equals p final. So it's just different letters that say the same thing. But what is this quantity? It's called impulse. And if we have a measurement of force with respect to time, so I push on something, I put a force on it, and I have force that goes into that over a certain amount of time, I'm going to add up the area under that curve, and that is what this integral does. Integral of f dt is the area under this curve. Now, if you don't like integrals, we can get pretty close to this with another form of the equation, which is mv1 plus an average force times a change in time, that equals mv2. Okay? And what that says is if we have an average force, or if we know the average force over our delta t here, then we can apply that and get pretty close to the final momentum. But can we use this in real life? Let's look at a real life example. So here at LeTourneau, we work with wheelchair research, and we help manufacturers make wheelchairs easier to use and more rugged, especially for developing countries. So I want to do a little experiment with this. When I get a wheelchair, I'm going to put a person in that. Okay. Hello, I'm a person. We're going to apply a force to the wheelchair, give it a push. I'm also going to measure where that wheelchair is with a laser sensor, so I can find out what the velocity is. Now, after I give this wheelchair a push, it's going to have a velocity, and we'll see if the impulse momentum equation describes where that is. So initially we'll have our velocity will be 0. Okay, then we're going to add a force for a lot of little seconds, and we're going to determine then where that new velocity should be. So let's go take a look.
One of my engineering students, Katie, helped me out with a test. First, we needed to weigh her in the wheelchair to find the mass. Now, don't worry, we don't broadcast the weight of our assistants on the World Wide Web. Of course, the mass of the object has a major effect on the velocity that the forces generate. A smaller mass will end up moving faster with the same amount of applied force than a bigger mass will. So now we are ready for the test. I will apply a force with the load cells to the handles of the wheelchair. I'm using 2 load cells because it's quite difficult to push the wheelchair in a straight direction with only 1 load cell. The laser device is measuring the distance to the white target on the wheelchair 50 times per second. So we can measure the velocity at any moment very precisely by observing the change in displacement every 50th of a second. Now I'll give her a push and record the force and displacement on the computer. Let's look at how these calculations work. If we have a weight of 180 pounds for the wheelchair and the rider, this equates to a mass of 5.59 slugs. Since we are starting from rest, our initial momentum is 0. Then, let's say we apply an instant constant force of 25 pounds for 1.2 seconds. This graph shows force on the vertical axis and time on the horizontal axis. This impulse should give us an increase of momentum, resulting in a velocity of 5.37 feet per second. However, in reality, forces are rarely instantaneous or constant. In our wheelchair example, the force measured by the load cells grows and peaks and drops to 0 when the load cells lose contact with the push plate. To determine the total impulse applied to the wheelchair, we will add both of these forces together. As I mentioned, we are recording force and position 50 times a second. So with a spreadsheet, we can easily add up the area under the force curve by multiplying each force reading times the sampling interval of 1/50th of a second. When we add all these little areas up, we get the area under the whole force curve, which is equivalent to taking the integral of f dt. This is the impulse. Now in this case, the impulse added up to 21.8 pound-seconds. To find the expected ending velocity, we divide both sides of the equation by the mass of 5.59 slugs. The velocity we would expect the wheelchair to have when the load cells lose contact with the push plate is 46.8 inches per second. So let's look at the velocity graph and see if that's what we got. Our laser measured the velocity starting out at about 0, and it rose sharply as we gave that wheelchair a push, and it got up to only about 41 inches per second. So this is not as high as what we predicted, the 46.8 inches per second. So why is that? Did we make a mistake in our calculations? Is the principle wrong? Well, let's take a closer look at the equation. There's a part of the impulse momentum equation I haven't mentioned yet, this summation sign. We need to take into account all significant forces acting on the wheelchair. My push was the main impulse on the wheelchair. Other impulses can come from wind blowing on the wheelchair, or gravity if the sidewalk is not level, and of course rolling resistance. Rolling resistance is a force coming from the interaction of the tire with the surface, and it makes a big impact on energy efficiency. We can clearly see the effect of rolling resistance when we look again at the velocity graph. The rolling resistance continues to apply its impulse after our applied force ends. Let's use the impulse momentum equation to actually estimate that rolling resistance force. Now, rather than predicting velocity by applying a known force like we did before, we will rearrange the average impulse equation and estimate the force by measuring the change in velocity. When you are doing design or research, it's really important to involve your customer early and often. I met Will in a local store and told him about the wheelchair research we do. He was very willing to help us out. As a young man, Will broke his back in a motorcycle accident. He's been riding a wheelchair ever since. While the load cells are useful for demonstrating a force impulse, as we saw, we really don't need them to quantify rolling resistance of a wheelchair. Now we will ask Will to give a single forward stroke to get the wheelchair going. After the stroke, rolling resistance will be a force acting on the wheels to slow down the wheelchair. By measuring time and the change in velocity, we can determine the average rolling resistance force. We did these tests with the rated tire pressure of 50 psi. But then we wondered what would happen if we lowered the tire pressure to 20 psi. We also did tests on carpet with the 50 psi pressure. Which do you think gave us the most rolling resistance? After the tests, we looked at the velocity graphs. The rolling resistance was obvious. Here's the velocity of the wheelchair with the full air pressure in the tires, shown over a period of 1 to 3 seconds. With tire pressure lowered to 20 psi, the velocity decreases more quickly. And on carpeting, the velocity decreases even more quickly, though the tires are full. Using the impulse momentum principle and the trend line for the velocity readings, we find the amount the velocity changes in 1 second for each condition. We multiply by the mass of 8.257 slugs for the rider in the chair to get the average force. It's interesting that to propel a wheelchair on a hard floor at full tire pressure, it takes about 3.4 pounds. If we lower the tire pressure to 20 psi, it takes another pound of force, or 30% more effort. Over carpet, it takes 2 pounds of force extra, which is another 60%. Now multiply that over hundreds of propulsion strokes a day, and it's easy to see that this can take a toll on a wheelchair rider. So it's clear that making a wheelchair easier to roll is important, and you can use science like the impulse momentum principle to improve products and change lives.